Okay, so welcome everybody. So this is SimVascular tutorial 13 on deformable wall simulations. So the way this tutorial is going to work, I'm going to give just kind of a brief, kind of 5-minute just motivation about what deformable simulations are, why we want to do them. Then I'll show you how to set them up in SimVascular. Okay. So first, what are deformable wall simulations? So I think at this point, especially if you're following along on YouTube with all of our tutorials, you've probably done some rigid wall simulations. So intuitively, what that means is that say you have your idealized blood vessel, or in other words, we call it a cylinder, and you're feeding blood through here. Okay. When we have a rigid wall, what that means is that this lateral surface right here, it doesn't move. Okay. And so the reason that this is kind of the default setting within SimVascular is that computationally and numerically, this is kind of one of the simplest things to do. So this is called the no slip boundary condition, where we assume the velocity goes to 0 at the wall. So while it's nice and convenient, as many of us know, that it's not really realistic. So if you compare this to someone in real life, if they actually had rigid blood vessels, we'd all be robots, and we wouldn't be able to move. It'd be kind of the same as you'd have plumbing made of iron in your body, which is not realistic. So your blood vessels are flexible, right? So this wall has to be able to move. Okay. And so to model this, the method that we use in SimVascular is known as fluid structure interaction. You'll probably hear the term FSI a lot, okay? And all that basically means is that, you have a fluid, which, for our case, 90% of the time is going to be blood, and then you have a solid, which is, the vessel wall, and those two are interacting, okay? And so, FSI kind of covers a very wide range of methods and techniques in order to kind of capture these interactions between fluids and solids. Okay? And so, to kind of, motivate, why is that, again, kind of why is that necessary in these cardiovascular simulations? I like to kind of draw an analogy. So let's say, let's go back to a simpler time. So let's say that, you're on a playground. Okay. Okay. So this is you and your best friend on the playground. Okay. And you're riding a seesaw. Okay. And so what do you know about the seesaw? So most seesaws are typically pretty rigid. So they're made of wood, which is typically a pretty rigid feature. Okay. And so what happens when you have a rigid structure like this, when one person goes down, immediately the other person goes up, right? So I'm going to characterize this in kind of a strange way, but it'll kind of make sense as we go. We kind of bring this back to cardiovascular simulations. So one way that we can describe this is that information of events happening at the left side travels to the right at an instantaneous speed. Or in other words, when something happens on the left side, the right side knows about it immediately because the structure is rigid, right? So let's contrast that, okay? And so let's say that we have our seesaw, but we can use the magic of digital things, okay? So let's say that we have a red seesaw now, and for some reason, red indicates rubber, okay? I don't know why I picked red. It was just kind of the first color that kind of stood out to me. But we have basically something that's going to be flexible. So this is kind of more similar to what we have in our blood vessels, which are flexible structures. Okay, so let's draw us again. Don't ask me why you're standing on top of the seesaw. You're too young to understand safety regulations. Okay, but when you have a rubber structure, what happens when you go down, right? Because the rubber is flexible, it doesn't immediately. You don't immediately react on the right side, right? So what's going to happen? So let's use purple for this, okay? is that, eventually, the right side is going to feel the effects of the left side, but it's going to take some time, right? Because immediately what happens when you push it down is that the rubber is not going to transmit that information. It itself is going to deform, right? And so that's what you see right here. So that you kind of have this little bit deflection right here, okay? So kind of immediately after you step down on this rubber seesaw, you have this little deflection, okay? And then as time goes on, then that deflection propagates down to the right side. And then eventually the person on the right side, gets launched up to the moon and you never see your friend again, okay? And so, what's happening here is that information is traveling at a finite speed, okay? And so this is a really important phenomenon in cardiovascular fluid mechanics. And the kind of the formal name for this is wave propagation. So wave propagation is an essential feature. And so basically what that means is that, every time your heart pumps or anytime something happens upstream, all your downstream vessels in like your head and your fingers and your toes, they don't feel what happens in your heart right away because all the vessels leading up to there are flexible, okay? So your heart will pump and it'll send a pressure wave down to your system, but it's not going to travel at an infinite speed. So that pressure wave kind of takes some time to reach there. And it's a time scale that's kind of independent of the flow. Okay? It's definitely kind of a weird concept to grasp at first because it's not like the pressure is traveling with the blood. Okay? It's traveling kind of at its own independent speed, and it's traveling along the walls. Okay? But it's not instantaneous, so it has some kind of finite speed. Okay? And the only way that you're going to capture this wave propagation phenomenon in your simulations is if you use a deformable wall. Okay, so let's see how we set this up in SimVascular. Okay, so now I'm switched over to my laptop screen. Okay, so here I have SimVascular open. Okay, so the nice thing about deformable wall simulations is that a lot of it's built into the GUI, so you don't have to do any coding yourself. But the prerequisite, the first thing that you have to do before you actually run deformable wall simulations is to actually run a rigid wall simulation first, okay? And I know that sounds strange, if our end goal is a deformable wall, why do we need to run a rigid wall simulation to begin with? And the reason for that is because, because you have so much going on with the deformable wall simulations, you have the fluid structure interaction, you kind of need to start from like a stable state. And so that stable state can be given to you from a rigid simulation because, you don't want to start from a case where like the velocities and the pressures all start out at zero, which is the default if you're kind of running a simulation from scratch in SimVascular, right? So you don't really want to do that for a deformable wall simulation. Otherwise, the simulation might diverge, okay? So your first step is to run a rigid, which I have right here. So I ran this, earlier, so, we don't have to go through it. And you can see right here, when you go to the wall properties, our wall property type is rigid, okay? So I've already ran these simulations, so we don't have to look at it again, okay? But, I want to bring your attention to kind of the most important step here is that when you convert your results, basically when you convert your results to a format that can be read by peer review, you need to check mark this one. So this, what this option will allow you to do is that it'll post-process the last step or the solution at the last time step of your rigid simulation as a restart file. Okay? And so this is extremely important, especially if you're running these simulations on the cluster in order to set this up properly. Because when you run simulations on the cluster, basically the domain is going to be split up among a bunch of different processors, and then you need to combine them into a single restart file in order for you to start the next simulation. Okay, so you go ahead and click convert. I'm not going to do this because I already did it earlier. Okay, but just like you did before, you can go select your folder and it'll convert. Okay, and then in order to check that the results converted correctly, you can go to the folder where you post-process your results, and you can see we have all of our VTP and VTU files here. Okay? But at the very bottom right here, you see that we have a restart file. Okay? So in this particular case, this is just a tutorial cylinder. So I ran it only for 200 time steps. So you can see we have a restart.200.0. Okay. So this 200 right here corresponds to the last time step of your rigid simulation. Okay. And the 0 right here indicates that it's a compiled result. Okay. So it's basically it basically contains your entire domain. Okay. You want to make sure that the 0 is here. Okay. So if you have something where this is like a 1 or a 2 or like a 5, then there's probably something wrong. So you want to basically make sure you come back here and make sure this is checked off. Okay. Okay. So now let's go ahead and set up a deformable wall simulation. Okay. And so to kind of fast track this, I'm going to make use of the copy and paste. Okay. Because I want to keep most of the simulation parameters the same. The only thing I want to change is just the wall properties and a couple other parameters that I'll let you know. Okay. So let's go ahead and right click on steady. Okay. And then go ahead and click copy. Okay. And then we'll right click again and then click paste. Okay. So you can see here we have a steady copy. Okay. So this basically is a simulation job using the same model, same mesh, with all the same parameters. Okay. So let's go ahead and rename it just to give it a better name. So I'm going to show you how to do two different kinds of deformable wall simulation. One with a constant material properties, where basically the stiffness and the thickness of the vessel wall is uniform all throughout. Okay, and I'm going to show you one with variable wall. Okay, so the first one I'm going to show you is constant, just because it's a little bit easier to set up. And basically what that's going to do is that it's going to allow us to specify a Young's modulus and a thickness throughout the entire vessel. Okay, so let's go ahead and double click this. Okay, and let's run through kind of each of the different, or basically everything that we need to change for the deformable wall simulations relative to our rigid. Okay, so the first thing that we have to do is we have to come to this tab called basic parameters. Okay, and you'll notice we have our fluid density or fluid viscosity, which are default set to blood. So the thing that we're going to change in this one is that we're going to need to specify an IC file. Okay, so IC stands for initial condition. Okay, so let's go ahead and double click this. Okay? If you're having trouble double clicking this, you'll need to double click the actual box that says IC file. Okay, and then what you need to do is you need to find the restart in our case it was restart.200.0. And that will provide the initial condition. Because remember, we want to start our deformable wall simulations from a stable place. So here I've used my Windows Explorer to basically locate that file. Let's go ahead and double click that. Okay. And we've successfully uploaded our initial condition file. Okay. So another thing you can do is you can specify an initial pressure here. So that's the pressure that will be at the start of your simulation. So it's not required, but if you want, you can set this to be something. So since I know what I'm going to do for this tutorial, I'm going to set it to that. Okay, and the initial velocities we can leave alone. Okay. So the inlet and outlet BCs. So in this case, I'm not going to change them just for the sake of brevity. But if you're tuning your simulation to match some clinical targets or to hit some data. Changing to a deformable wall simulation will affect your results. So, you might have to change these boundary conditions in order to make sure that your simulation results are consistent with the data that you have. But for now, just for the sake of brevity, I'm just going to leave these alone. Okay, so now for the big, changes. Okay, so most of the changes that you're going to make for deformable wall simulations are going to take place in the wall properties tab. Okay. So instead of rigid, you can see we have two different options here. So deformable constant, deformable variable. So let's go ahead and click deformable constant. Okay. And you can see a lot of new data entry things have come up. Okay. So it's going to ask you for the thickness of the vessel wall, the elastic modulus. Okay. Poisson's ratio and shear constant, you can just leave those alone. So the default values are fine for that. Okay. It's going to ask you for the density of the vessel wall and also for the initial pressure. Okay. So let's start with the thickness. So the thickness is literally just the thickness of the vessel wall. So, if you took out a blood vessel from your body and you kind of took a caliper and kind of measured it like this, that's the thickness that you would measure. Okay. And so, the question that I get, all the time is, how do we specify these parameters for the vessel wall? Okay. So that's an excellent question. So, in reality, if you're working on a specific part of the body, and you can look up in the literature about, some experiments or some measurements that people have taken of the thickness and the elastic modulus in those areas, you can definitely use those. Okay? But if not, you're going to have to make some assumptions. And, the reality is for a lot of places, you're going to have to make some assumptions. Okay? So for thickness, thankfully, there is a pretty reasonable assumption that we can make. Okay? So generally for the thicknesses, for blood vessels, one good kind of rule of thumb or, a reasonable estimate is to assume the thickness is 10% of the vessel radius. Okay? So if in this case, we just have a cylinder, so it's just a constant radius. So if you know the radius of your cylinder or your blood vessel, you can basically just take 10% of that and input that as the thickness. Okay? And so for this case, since I've already kind of prepared this example, we're going to use a thickness of 0.2. Okay. The elastic modulus is going to be a lot more difficult to find, and what that defines basically, if a lot of you guys have backgrounds in mechanical engineering or civil engineering, this defines basically the stress strain response. Okay? And so what that means is that it defines how much the material, in this case the vessel wall, is going to deform when you stress it or when you apply some force to it. Okay? So these are difficult because there's very limited measurements that occur. So you might find some cadaver measurements out there, but those aren't going to be totally reliable. Okay? So here you're going to have to make some assumptions. You might have to kind of cross-reference between a few different literature sources. Okay? But in this case, I'm going to use a elastic modulus of 0.4 megapascal. Okay? And you'll notice here that I put 4 million. Okay. So that doesn't sound like 0.4 megapascal. So 0.4 megapascal should be 400,000, just like that. Okay. But remember, the default units in SimVascular are CGS units. Okay. And so to convert between megapascals and CGS units or in this case, it's pressure, you just multiply by 10. Okay. So a 0.4 megapascal is going to be 4 million dyne per centimeter square. Okay, so that for the density, we're just going to assume a density of 1. Okay, so for most of the time, that's pretty reasonable. Okay, and for the pressure, end of the day, you just have to input a pressure that's going to be physiologically, realistic. But kind of the best way to do this is to examine your rigid results and to input a pressure that's kind of that kind of matches your rigid results. So, if you can view your rigid results in ParaView, or you've post-processed them already, and kind of the average pressure in your entire domain, you can input that pressure here. But any physiologically relevant pressure will work. So in this case, I'm just going to use a pressure of 100 millimeter mercury. So that's 1,333 times 100. Okay, it's 133,000. Brain fart. Okay. So the next thing we're going to set is our solver parameters. So most of this we're going to keep the same. Okay. I mean, in reality, you might want to change this. Specifically the time step size. You might want to make that smaller because deformable wall simulations are a little bit more difficult to converge. Okay. But the only thing that I really want to stress you guys to actually change is the linear solver settings. Okay. So the default settings for the linear solver are what's called the NS solver. So NS stands for Navier-Stokes, basically. Okay. So the NS solver works fantastic for rigid simulations, but for deformable wall simulations, it actually it really starts to struggle a little bit. So what we generally recommend for if you're running deformable wall simulations is to switch the linear solver to GM-Res. Okay? Don't ask me what that stands for because I forgot. Okay, and then after you switch to GM-Res, we need to change the tolerances on the results. Okay, so these default tolerances, these work great if you're running the simulation on your desktop. But if you're running deformable wall simulations, you really want to make sure that you get some accurate results. So you really want to tighten up these tolerances quite a bit. Okay. So I'm going to give you some example values here, but of course, you can make these even more strict if you want. Okay. So I'm basically making the tolerance as 0.01. Okay. And then the last thing that this is just kind of a personal thing for me, but you know, I know not everyone does this, is I like to make sure that the linear solver can iterate enough in order to reach a converged solution. Okay? And so the way that I do that is I change this number right here. So what this number sets is basically the amount of iterations an outer loop does inside the linear solver. So right now it's only doing one outer loop. So I usually like to change this to 10. So it does kind of 10 outer loops. And then inside this outer loop, it does kind of some several ones like this. So that kind of makes sure that, to me, this kind of makes sure that your results are kind of converged within every time step. Okay. Okay. And so now that that's done, so let's go ahead and create our simulation files. Okay. Okay. So that was really fast. So normally, you know, if you have a mesh that's, you know, much bigger than this one, I think this mesh is only about 45,000 elements. It's going to take a lot longer. Okay. So let's so now that the pre-solver is done, let's go ahead and check it out. Okay. So if you go, you know, again, I'm on Windows. You know, on Linux you can find the same thing, and on Mac. Okay. So let's go to our simulation folder. So, you know, we know that we've called our job deformable constant. So I'm in the deformable constant folder. Okay. So you can see, you know, after you've created your simulation files, all the usual suspects are here, you know, to run your simulation, except, you know, we have a couple extra files. Okay. So the one extra file that I want you to take a look at is this one right here called displacement. So it's a VTP file. So you're going to go ahead and open this up in pair view. Okay. Okay. So you can see once you open up the displacement file, you know, here's your cylinder. So right now it's colored by global element ID. Okay. And then one thing that you can view is the actual displacement field. So, you know, because we're doing a deformable wall simulation, you know, our walls are going to deform a little bit. And what this field shows you is kind of the initial field. So this is kind of the starting displacement field that we're going to run our simulation with. Okay. Excuse me. So remember when I talked about earlier that, you know, you want to start a deformable wall simulation from a stable case. Okay? And so, you know, while that's true for velocity and pressure, which is what we got from our rigid simulation, that's also true for the displacements as well. So we want to make sure our displacement starts from a place of, you know, relative equilibrium. Okay. And so what's actually happening under the hood when you do a deformable wall simulation and you create, you know, you click create data files for simulations, SimVascular is actually, you know, computing an initial displacement field by literally inflating your model. Okay? So if you imagine your model is kind of like a very weirdly shaped balloon, okay? And it's a balloon where it's, you know, clamped on kind of this on the ends right here, okay? And it's basically going to apply some pressure, and then that pressure is going to slowly inflate your domain like that. Okay? And so if you want to visually see the displacement, okay, I use this this filter in pair view right here called warp by vector. Okay. So let's go ahead and hit apply because we're going to warp by our displacement vector here. Okay. And you can see that our model is kind of puffed up a little bit. Okay. And that's kind of our initial displacement field right there. Okay? So let me kind of you know, do a little, you know, switcheroo here so you can see. Okay? So this is our kind of our rigid model. So this with no inflation. And then after we inflate it, it kind of looks like this. So you can kind of see it kind of it's kind of inflated a little bit just like that. Okay. Okay. And then once that's done, you know, you're basically ready to go. So you know, if you want to run the simulation on your desktop, you can go ahead and click Run Simulation. But for most practical cases, you're going to want to run these simulations on the cluster. So you can basically, you know, just like you always have, you can ship these files out to a cluster where you can run the simulation. Okay, and it's going to be the same file. So the displacement file is it's not a necessary input. It's kind of just there for you just to check the initial displacement field, you know, just to make sure things are okay. Okay, so that's a deformable wall simulation with a constant material property. So let's see how we set up one with a variable wall. Okay, so I'm going to use the same copy paste because I'm lazy. Okay, so this time we're going to copy and paste the you know, our deformable wall simulation because our variable wall is going to be very similar. Let's go ahead and rename this. Okay. All right. So now we're going to do we're going to set up a variable wall simulation. So just like, you know, just like we did for our constant wall, we need to specify our IC file. So in this case, it's already set because we just copied it. But if you're going to be doing this, without a constant material property, you can, make sure you set this up. Okay, and it's definitely not a prerequisite to run a constant wall material property, simulation first. So you can jump straight from a rigid wall to a variable wall material properties, and that's very common too. But if you're going to do that, just make sure you specify this IC file right here. Okay? And outlet BCs, again, we're going to keep this the same. But again, remember, if you're doing this for something practical, you might have to change those just to make sure you get the simulation results that you want. Okay, so now we come to wall properties. Okay, so instead of deformable constant, we're going to switch to deformable variable. Okay, so you can see, things have changed a little bit. Okay, so instead of specifying a thickness and a elastic modulus for the entire model, we're instead given this kind of table format where we can specify the thickness and elastic modulus for each of the different surfaces in our model. Okay? So in this case, we have a very simple model. It's just a cylinder. So we just have 3 surfaces. We have the lateral wall. We have the inlet, which could be this one or that one, and the outlet, which could be this one or that one. Okay? So typically, the way, and of course, special cases exist, but kind of the typical use case for deformable wall simulation is that you specify the material properties at the caps, okay, and they can be set to different values, as long as they're physically realistic. And then on the walls, what you're going to do is you're going to leave it blank, and you're going to kind of let SimVascular kind of fill in the blanks in between the different caps. So what you're going to have is a smooth transition of material properties from one cap to another, or if you have a complex model, from all the different caps to all the other ones. Okay. So just to kind of illustrate this, I'm going to give it material properties that are similar, to what we did before, but not exactly the same. Okay. So you can see, at the outlet, which could be either of these, I've specified a thickness of 0.2. And at the inlet, I've specified a thickness of 0.15. Okay. And then with the Young's modulus, I've kind of switched them up too. Okay. So remember when I talked about earlier, the thickness, is typically specified as 10% of the vessel radius. Okay. So if you have a model that's really complex with a lot of different vessels, different sizes, it can be really hard to pick one radius to kind of represent the entire model. You can find an average, of course, but a lot of times that's not going to describe a really complex model, especially when you have like a big chunky aorta and like the tiny slender coronaries. So picking shooting kind of in between those two doesn't really seem that good a lot of the time. So with the variable wall properties, what you can do is you can specify the thickness at each of the different caps, okay, where this thickness can be the 10% of the local radius of that cap, okay, and then you can basically let SimVascular kind of figure out the rest. Okay? And so what you'll get is kind of a smooth transition of thicknesses from something that might be really small at your small outlets to something that's really big at your big inlets or outlets. Okay, and this will be more realistic than kind of a constant material property one. Okay. And so same thing with the elastic modulus. So if you know for sure that a certain kind of vessel has a certain elastic modulus, you can specify that. But if you have a certain other kind of vessel in your model that has another kind of elastic modulus, you can specify that as well. Okay. So for the solver parameters, we're going to keep everything the same. Okay. And then just like we did before, we're going to create data files. Okay. So this should be pretty quick because it's a pretty simple model. Okay. And so once that's done, you go into your folder. Okay. So you can see all the usual suspects to, after completing the Presolver are done. So because we're doing a deformable wall simulation, we have our displacement.vtp. So that's the same as constant. But you can see we have one more, person that decided to join the party, which is this varwallprop.vtp. Okay. So let's go ahead and open this guy up in pair view just so you guys can see. Okay. So here's our cylinder, okay? And then, if you check the vector fields, or or in this case, they're scalar fields, you can see we have fields for thickness and Young's modulus. So let's look at the thickness first. Okay? So if you look at kind of the color legend here, so we have a maximum of 0.2
and a minimum of 0.15, okay? And you can see, and remember, those are the thicknesses that we specified at the inlet and the outlet, okay? And you can see, we have 0.2 here, 0.15 here, and then we have kind of a smooth transition in between the two, in between them, okay? So this is what the variable wall property solver will do. You'll specify your material properties at the caps, and then everywhere else, basically, you have kind of a smooth transition in between the two, okay? If you kind of want to know what's happening underneath the hood, basically, we're solving a Poisson's equation for the thickness and the Young's modulus distribution. Okay, and so here's our elastic modulus. So remember, we specified an elastic modulus of 4 million on one end and then 3.5 million on the other. And again, what you see here is a smooth transition from here, the high here, and the low there. Okay. Okay. And so once you basically verify that the material properties they look, the way that you want them to look, and your displacements, they look reasonable, you can go ahead and run the simulation. Okay. So if you want to run it on your personal machine, you can go ahead and do that here. But again, if you want to run on the cluster, probably a lot of you kind of know how to do that already. Okay. Okay. And so that concludes the tutorial on deformable wall simulations.